The Gulf Coast of Florida. This lush setting is the only U.S. habitat for a peaceful, friendly sea mammal, the manatee. Manatees are inquisitive, slow-moving creatures. Their curiosity and a tendency to swim near the surface of the water brings them into frequent contact with humans.
This manatee here is using a line that we call the dental flossing line for manatees. If you're not real careful when you start your motor, you could inadvertently end up injuring one of these beautiful animals.
Encounters with humans have endangered the manatee population here. Nearly all bear lasting scars from powerboat propellers, and each year, increasing numbers are killed. How can the increase in manatee deaths be explained? Are people behaving differently now than they have in the past?
Yeah, right trunk.
Statistics can help us answer these questions and can point towards solutions that will protect manatees and their young. In this unit, we plumb the depths off the Florida coast in order to explore new statistical ground. Instead of looking at situations involving single variables, we'll begin to explore the relationship between two variables, like manatees and powerboats. We'll learn that when both variables are quantitative, that is, we can plot them on a graph and do arithmetic, a scatter plot is the right display. We'll see that not all variables are created equal. When one variable accounts for changes in another variable, the first is called the explanatory variable, while the second is called the response variable. We'll look for patterns in the data on a scatter plot and also try to explain points that fall outside those patterns. We'll learn a new technique called a median trace that can be used to bring out a pattern in a scatter plot that might otherwise be hidden. In the wintertime, the Florida manatees migrate to warm water areas. The waste heat outlet channel of this power plant is a prime gathering spot. A biologist takes photographs. This is one of the ways to estimate the total size of the manatee population. But because manatees concentrate in a few small areas, they're vulnerable to human activity, particularly the use of powerboats. In an effort to protect the manatee, the state has imposed speed limits in key areas.
Skipper, take your boat out of gear. I'll be coming on your port side. Y'all gonna have to be more conscientious of this manatee zone. That's too fast in there. I know you don't want to hit one of them. I'm sure you don't want to do that, all right? Watch your water. A good way to tell is you look at the back of your boat. If you're peeling off that white water off the back of the boat, it's too fast. You need to get it down to an idle speed.
Here are the data on powerboat registrations and manatees killed by boats for the years 1977 to 1987. Both boat registrations and manatee deaths are quantitative variables. A quantitative variable is measured numerically, which means that we can plot the values and do arithmetic with them. Height in inches is also a quantitative variable. Hair color, black, blonde, and so on, is not. When we're examining a situation involving two variables, and both are quantitative, we can use a graph called a scatter plot. To make a scatter plot, we first draw a horizontal and a vertical axis. But which variable should we put on which axis? Sometimes it doesn't matter, but in this case, it does. We believe that the number of powerboats in the water helps explain the number of manatees killed. So we call the number of powerboats the explanatory variable. The explanatory variable always goes on the horizontal axis of the scatter plot. Here, that's powerboat registrations, which we're showing in hundred thousands. We choose boat registrations as the explanatory variable because we expect that the more boats that are in the water, the more manatees will be killed, everything else being equal. Or, to put it another way, we assume that the number of manatees killed is a response to the number of powerboats in the water. So we call the number of manatees killed the response variable and plot it on the vertical axis. The number of registrations in 1977 was 447,000, and the number of manatees killed was 13. In 1978, there were 460,000 registrations and 21 manatees killed. In 1979, 481,000 boats were registered, and 24 manatees were killed. We continue plotting the points for all the data we have, and we come up with a picture like this. Now, what does this scatter plot tell us? The data confirm our suspicions. As the number of boat registrations went up, so did the number of manatees killed. The lower left to upper right pattern of the points show that as ever more boats crowd Florida's waters, manatees will be in increasing danger. The state of Florida is responding to the problem. In addition to stricter enforcement of speed limits, state officials have proposed a new protection plan limiting the number of boat docks. That means fewer boats.
The factors in Florida that are causing these deaths are on the increase, and the factors are related to development, increased numbers of people using the water. The problems the animals face are directly related to the growth of the state, and we have to accommodate the animals as we accommodate the human growth. And they're extremely adaptable animals. They're tough, they're resilient. If we just give them a chance, I think we can keep them around.
Whenever we look at a graph, we first look for a pattern in the data. The manatee data exhibit a clear pattern, a clear relationship between the variables. As boat registrations increase, the number of manatees killed increases as well. This is called a positive association. Now, this is clearly not positive for the manatees, but it is positive in a statistical sense. As one variable increases, so does the other. Sometimes data exhibit a negative association. In this kind of relationship, as one variable increases, the other decreases. Learning is a classic example of a negative association. Let's look at the relationship between, say, how long it takes you to make a pie and the number of times you make one. The amount of time it takes to make a pie is the response variable, and the number of times you make one is the explanatory variable. We find that as the number of times you make a pie increases, the amount of time it takes you to make one decreases. So we say the two variables exhibit a negative association. You'll notice another thing about the manatee data. Most of the points fall along a straight line. We call this, for obvious reasons, a linear pattern. Now, we can't expect all of the points to fall exactly on a straight line. Actual figures are rarely so cooperative. But we can call a pattern linear if the data points fall roughly along a line. Other patterns in data are also possible. This graph shows a curving relationship between two variables. It suggests that the variables increase together until one increases faster than the other. The important thing is to look for patterns in scatterplot data, because any strong pattern, whether linear or curved or something else, helps us interpret data in powerful ways. So the key is to be able to recognize a pattern when it exists. Now, what about those points that don't fit so well? Once you've described the overall pattern of a scatterplot, it's important to identify individual points like this one that clearly lie outside the overall pattern. These points are called outliers. An outlier has to be explained. Sometimes it's simply a mistake. You recorded the data incorrectly or made a mistake in drawing the plot. When it's correct, though, an outlier may point to something unusual that you want to know about. Suppose this is a plot of lake temperature readings in an active volcano region in Hawaii. This one is much hotter. It could mean that the sensor is broken, or it could indicate the volcano is about to blow. Investigating this outlier could profoundly affect the people who live in the surrounding towns. So far, the scatter plots we've seen have shown a clear pattern. What about this one? To the eye, it appears to be a haphazard scatter of dots. There's no apparent relationship between the two variables. But in fact, a relationship does exist, one that caused a scandal in 1970. In that year, the United States was engaged in a long war in Vietnam that deeply divided the American people. Not all of the men who fought in that conflict chose to serve as they do now. Most were drafted and required by law to go to war. Congress designed a supposedly random lottery procedure to determine who would go to Vietnam. The 366 possible birth dates were placed in capsules and drawn at random from a bin, and assigned selection numbers in the order drawn.
September 14th.
The first birth date chosen was assigned selection number 001, the second selection number 002, and so on. Men whose birth date matched selection number 1 were drafted first. This scatter plot shows the outcome of the 1970 draft lottery. The explanatory variable, plotted as usual on the horizontal axis, is the date of birth. The response variable is the draft number, numbered 1 to 366. Remember, the lower his number, the more likely a young man was to be drafted. There is a pattern in these data, but to see it more clearly, we need to supplement the graph with a numerical calculation. We're going to use what we know about describing a single variable to get to a technique called the median trace. First, we'll slice this data into 1-month increments. We draw a box plot for January's data, which shows the 2 quartiles on either side of the median draft number for men born that month. We make similar box plots for all of the months in the year. Next, we indicate the median for each month with a dot. Connecting the medians gives us the median trace for these data. We can now see the pattern that was hidden before. The medians show a clear downward trend. Later months have lower median draft numbers than earlier months, which means that men born late in the year were more likely to be drafted and sent to Vietnam than those born earlier in the year. The problem with the 1970 lottery was that the birth date capsules were not thoroughly mixed. The December dates remained closer to the top, and therefore were more likely to be selected first.
December 30th.
December 30?
003.
December 7.
To avoid this problem in 1971, statisticians from the National Bureau of Standards designed a new procedure. 2 drums were used, one containing birth dates, the other selection numbers. The capsules in both drums were thoroughly mixed, and then randomly drawn birth dates were paired with randomly drawn selection numbers. Here's the median trace of the 1971 lottery compared to that of the 1970 lottery. The median draft numbers do vary up and down from month to month, but there is no systematic trend in that variation, so it can be attributed to chance. From this data, we can see that the 1971 lottery was truly random and fair. In this unit, we've used the scatter plot to look at the relationship between 2 quantitative variables. We've approached the scatter plot as we would any graph, looking for an overall pattern and then identifying outliers, deviations from that pattern. And we've added a numerical calculation, in this case the median trace, to help detect a pattern that exists in the scatter plot data.